Okay, good morning. So the plan for today is to discuss sampling distributions in the central limit theorem. We just wrapped up our discussions in chapter 6 of dealing with the standard normal distribution and general normal distributions. Went through lots of examples of those, and hopefully you're feeling pretty confident with that material. As I mentioned in the past couple of lectures, that material is really foundational for really most of the rest of the course. The something like the strong majority of problems that we will be doing from here on out will involve some kind of normal distribution calculation or lookup, or something that's qualitatively similar. Maybe it's a t distribution or a chi-square distribution in the future, but it's a very similar idea anyway. So really taking the time, putting in the effort to master this material from the last couple of sections is really a worthwhile endeavor. So that is our goal for today, to finish up sampling distributions in the central limit theorem. And that will conclude our in-class discussion on chapter 6. I've bumped part of chapter 6, last little bit testing for normality, to a supplement. It is posted in 2 parts on the YouTube playlist. So when I originally posted it, because I pulled it from a previous semester, it kind of like went at the bottom of the playlist. I think I resorted it so that it's at the top of the playlist now, like where they've been being added. But if you don't see it at whatever end of the playlist you're used to seeing it, look at the other end of the playlist. It should be pretty clearly labeled. So 2-part supplement there. I think one is about 15 minutes and one is about maybe 50 minutes, 50 minutes or so. So about an hour or so in total between the 2 pieces. And then either starting today or starting next week, we will jump into chapter 7 confidence intervals. And chapter 7 and 8 is something like the culmination of the course. Not quite. We have a few topics after that, but it's really where we start to see our empirical ideas from maybe chapters 2 and 3, and our more philosophical, abstract mathematical ideas from chapters 4, 5, and 6 kind of marry together and really allow us to take things like descriptive statistics, which were just more explanatory, this is what I see in the data, and turn those into inferential statistics, saying, okay, I think that I might understand something a little more deeply about how the world works, or how this process works, or how this population behaves. When I make such a statement, I can make it with lower confidence. I can say, for this data set of size 40 or something, this is the mean, period, end of story, no arguments. But when I'm making an inference, there are some arguments to be had. But on the other hand, making an inference is much more helpful, provided that we make it well. So that's really what we start into in chapter 7, is really talking about inferential statistics in chapter 7 and 8. So if we don't get to it today, I would strongly recommend reading through the first couple of sections of chapter 7, taking kind of a quick skim through those so that you know what the ideas are that we're going to be addressing in the next several classes. Okay, the quote of the day today, but my window is a little wonky here. Let me move this over a little bit. There we go. The quote of the day today is really just an idea. It's the idea of exchange value for value. When you're looking to transact with somebody, if you're asking for something from them, make sure that you're providing something of equal value to them. This, if you think of this as something like a life principle, it has a lot of benefits. It essentially makes it nearly impossible for you to get scammed, because most scams start out with, hey, I'm giving you this thing for free, right? Like, hey, I'm a Nigerian prince, and if you send me $1,000 to get out of the country, then I'll give you a free, $1 million or something. It's like, well, that's not what did I do to earn that $1 million? I'm not providing $1 million worth of value to this person. So a lot of scams start off with, I'm willing to give you something where you don't have to give me anything, or you have to give me little in return. But further than that, a little more maybe direct than that is, well, when you graduate with your degree and you're out looking for a job, you're putting yourself on the job market and you're asking an employer to pay you a certain amount of money per year, right? If you're asking them to pay you, you know, 50, 60, $70,000 per year, that's, you know, a couple of brand new cars per year. I mean, you know, presuming you're not driving Ferraris or something. And you know, that's a non-trivial amount of value you're asking them to provide. Ask yourself what value you're providing in return, or how could I provide a potential future employer a greater value, right? What could I do? Maybe what coursework could you take that they would find more valuable, that would help their business more, or maybe what ancillary training, or what as the soft skills. I think that's not the best way, not the way that people like to refer to them these days, but soft skills are super important. What kind of soft skills can you bring to the table? Things like fostering teamwork or encouragement or leadership, that can help them, that can be more valuable to them. And so I like this idea as well that's related. We want to exchange value for value, but we don't want to think of it as like a poker game with a zero-sum mindset, where for me to, you know, to be better off, somebody else has to be worse off. I think ideally, we would like to find ways to grow the pie, right? Um, if I get, you know, if I get say better at leadership or better at encouragement, something like that, maybe by me coming onto that team, everybody in my team is better for it. And, you know, maybe bringing somebody else onto our team, maybe I'm better for them being brought onto the team. So if we're all supporting each other that way, that can be a really powerful corporate culture to be part of. All right, so that is the idea for today. As I've said the last couple of classes, my allergies have really been acting up, even though I've doubled my allergy medication. But with all of the rain and freezing and thawing and all of that, I might have to pause the video a couple of times to handle my allergy situation, but try to make it through. Okay, so moving on in chapter 6, we're going to talk about sampling distributions and the central limit theorem. Okay, what's the idea of a sampling distribution? Well, let's kind of work through a motivating example and then talk about the idea of sampling distributions and see where this motivating example leads us in terms of the central limit theorem. So it is important to note, and I'll note this up front, this is a motivating example. This is not a proof of the central limit theorem. We're going through one very specific, carefully chosen and curated example where we see the central limit theorem's result kind of very clearly, but it's certainly not a proof of the central limit theorem. Okay, so let's start with an average number of heads on one flip of a coin, or let's actually just start with X, the number of heads on one flip of a fair coin. So when n equals 1, we're not really going to concern ourselves with an average number of heads on one flip. It's just really just the number of heads on one flip. And X could be, of course, 0 or 1. In other words, we could have flipped a tails or a heads on our single flip. If we flip a tails, we got 0 heads on one flip. Flip a heads, we got 1 head on one flip. And this happens with probability 1/2 and 1/2. It's a fair coin. And let's, so we have a probability distribution written out here. Let's find the mean and standard deviation. This will be a little bit of a review of some of the chapter 5 material. We'll see that again. So X times probability of X, 0 times 1/2 is 0, 1 times 1/2 is 1/2. And my expected value of X, or maybe what I'll call mu sub X, is 1/2. So the average number of heads on one flip of a coin is 1/2. That makes sense. And now on to find the variance standard deviation. We need X squared, which is 0 and 1. X squared times the probability. 0 times 1/2 is 0, 1 times 1/2 is 1/2. The sum gives me expected value of X squared, which is 1/2. And then I have that my variance of x is, well, that's expected value of x squared, 1/2, minus the mean squared, minus 1/2 squared. 1/2 minus 1/4 is 1/4. And my standard deviation of x is 1/2. Let me jump off to the side here. And let's consider our variable x relating to one flip of the coin. We know what its distribution looks like. There's 0, here's 1. Probability 1/2 for each of them. And we see that mu x is 1/2. And sigma x also 1/2. So I'm just going to kind of keep track of our results over here on the right side. Okay, so that should be, that shouldn't be very surprising to us. We should be able to do that. Now let's switch gears a little bit. Let's consider n equals 2 flips. Let me write out all of the sequences of 2 flips, heads or tails. I could get tails, tails. I could get heads, tails, tails, heads, or heads, heads. Those are my 4 distinct sequences, 4 distinct outcomes for 2 flips of a coin. Now, something that I might think of is, I might think of a random variable that looks like x bar, the average number of heads per flip. As a side note, we could go through and do all of this same stuff that we're doing here, except we could talk about the sum instead of the average. We could talk about the total number of heads per flip, or sorry, the total number of heads on n flips. And we would get something like the central limit theorem, but it would be a little harder to see the pattern. So that's why we're taking this step here. Okay, so this is going to give rise to something called a sampling distribution. Let's rewind a little bit. We've talked about this idea in the past, so I don't think this is a new idea, but I just want to remind us about it. It's a little bit abstract. If I was back in chapter 3, I give you a data set. Here's a data set of size 10. Compute x bar for this data set. That's not a random process. Everybody that does that should get the same x bar, the same result. But where did that data set come from? That data set was probably a sample taken randomly from a population, right? So if I have my data set to x bar, this is not random. This is what we call deterministic. If I hand everybody the same data set, you should all get the same x bar from it. However, over here, I have my population, and the process of getting this data was random. Which means if I told each of you, maybe we're looking at heights of people in Pittsburgh, if I told each of you, randomly sample 30 people in Pittsburgh, measure their heights, take that data set, then each one of you most likely is going to get a different data set where these are not the same. But with different data sets, you're probably going to get different x bars. These are probably not going to be the same. And what we see is that the randomness of sampling from the population implies essentially a randomness in this end result, the value of x bar that we calculate. X bar itself is like a random variable. Well, not like a random variable, it is a random variable. X bar being a random variable means that it has, for instance, a distribution. It has its own mean. The x bar random variable has a mean, and the x bar random variable has a standard deviation. Just like any other random variable has a mean or a standard deviation, so does this x bar random variable. That's what we're investigating here. Now, because I have a fairly small population, it's only two flips of a coin, I can actually enumerate all of the possible samples, right? I could have sampled flipping this coin twice and gotten a sample that looked like tails, tails, or one that looked like heads, tails, or one that looked like tails, heads, or one that looked like heads, heads. Those are all of the possible samples of size 2 that I could get from this essentially very small, very limited population, right? If we had a population of 1 million people and we're trying to select 30, there's tons and tons of possible samples we could get. We couldn't enumerate all of them. But this is a small enough problem, it's quite a small problem. We can enumerate all of the possible samples we could have gotten out of here, which means we can attack X bar, the random variable, directly. We can just say, these are all of the possibilities for X bar. We can figure out what is the distribution of X bar explicitly, and then from there we can find the mean of standard deviation. That's what we're going to do here. So in each one of these samples, I'll call this maybe X bar observed. Oh, I wrote that a little too low. Actually, I think I can just bump these down a little. Oh, I missed my top of my T there. And I just, all right, it's not happy with that. So we will just draw a new top of the T. All right. So I'll call these X bar observed maybe. If I got this sample, if I flipped this fair coin twice and got tails, tails, what would the average number of heads per flip be? Well, I got 0 heads on 2 flips. That's 0 out of 2. That is 0. If I got heads on the first flip, tails on the second, I got 1 head on 2 flips. That's an average of 1/2 of a head per tail, or per flip, 1/2 of a head per flip. Same with tails, heads. 1 head on 2 flips, average of 1/2 of a head per flip. And heads, heads, 2 heads on 2 flips, 2 halves, or 1 head per flip on average. These are all equally likely by design. I set up my tails, tails, heads, tails, tails, heads, and heads, heads, so that these were equally likely outcomes. Remember, this is a fair coin. So each of these, this 0, this first half, this second half, or this 1, are all equally likely. So they each occur with probability 1/4. Or I can come over here and I can look at my X bar, remembering this is a random variable. My X bar random variable has 3 possible outcomes: 0, 1/2, or 1. This X bar random variable has probabilities associated with its outcomes. 0 occurred 1 time out of 4 equally likely. 1 occurred 1 time out of 4 equally likely. And 1/2, that outcome occurred twice out of 4 equally likely times. That's 2/4 probability for it. I could write that as 1/2, but I'll leave it as 2/4 just to make it clear where things are coming from. So what do I have here? I have my distribution of the random variable X bar. Remember, the idea here is that X bar, the sample mean, is a random variable because we're randomly sampling from the population. In this case, we're flipping this coin, and which of these 4 scenarios we end up in is random. It's dependent on which flip of the coin we get on flips 1 and 2. Okay, well, I guess I can compute the mean of this distribution now. This distribution of some random variable has a mean. How do I compute a mean? I multiply the outcome times its probability. My random variable is now called X bar, but that's just the name of my random variable. I could call it Y or Z or something instead if I wanted to, but it's just called X bar. So I just multiply my outcome of my random variable times its probability. 0 times 1/4 is 0. 1/2 times 2/4 is 1/4. 1 times 1/4 is 1/4. And now I can say something like the expected value of my random variable. What's my random variable's name? X bar. The expected value of X bar is 1/4 plus 1/4 or 1/2. And maybe I call that, instead of like mu sub x up here, maybe I call this mu subscript x bar. So I have my distribution here. I'll kind of block off the important things. My distribution of the random variable. And now I know my random variable's mean. The name of my random variable is x bar. And I want to find its variance and standard deviation as well. So I need to square my outcomes of my random variable. 0 squares to 0, 1 squares to 1, 1/2 squares to 1/4. And then I multiply outcome squared times probability. 0 times 1/4 is 0. 1 times 1/4 is 1/4. And then 1/4 times 2/4 gives me 2/16 or 1/8. 1/4 is 2/8. This is x bar squared, probability x bar. So the expected value of x bar squared is 3/8. And then I see that my variance of this random variable, the variance of x bar, is what? It's going to be expected value of x bar squared, that's 3/8, minus the mean squared, minus 1/2 squared. That's 3/8 minus 1/4, or 3/8 minus 2/8 is 1/8 for the variance. And then lastly, I have the standard deviation of my variable, which I'll write as sigma subscript x bar, is 1 over square root of 8, or that's 1 over 2 root 2. I'll choose to write this as 1/2 times 1 over root 2. And that is my third important piece. Okay, so let's come back up here and add this to the list. So this is like n equals 1 kind of. So x bar for 2 flips for n equals 2. I see 3 things. My distribution has changed a little bit. I can get 0 and half or 1 as outcomes, and they occur with ratio 1 to 2 to 1. So my distribution gets squeezed a little bit more into the middle. My mean, mu x bar, is still 1/2. And my standard deviation, sigma x bar, when n is 2, is 1/2 times 1 over root 2. Let me erase some of this work over here so that I've got enough room to add the n equals 3 information a little bit later. Okay. So I've got 1 flip, 2 flips. Let's go to 3 flips. 3 flips, we still have a small enough sample space that we can just enumerate all the outcomes and really just brute force what the distribution of x bar is. So we're basically doing the same thing we did up here, same process, same idea, but with 3 flips. So for 3 flips, I could have tails, 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 heads, tails, 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 heads, or tails, heads, heads. So those are all the possibilities, with the first flip being tails, and then I just make the first flip heads and repeat the other two, repeat that sequence. So heads, tails, tails, heads, heads, tails, heads, tails, heads, 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 heads. So these are my 8 outcomes. I did it kind of systematically, and so that way I made sure I didn't miss any or double count any. Just like above, I can think of X bar as being the average number of heads, but in this case, on 3 flips. Of course, still of a fair coin. So here we have 3 flips. And what's my observed value of X bar? Why do I keep writing my X bar observed line too low? Okay. Well, for 3 tails, I got 0 heads out of 3 flips. That's 0 out of 3, or an average number of heads per flip. Average number of heads, this is per flip on 3 flips. Average of 0 heads per flip on 3 flips. Tails, heads, tails, I got 1 head on 3 flips, so 1/3, 1/3, and then 2/3 for this one with 2 heads on 3 flips. 1/3, 2/3, 2/3, and then 3 heads on 3 flips is 3/3 or 1 head per flip on average. Okay, this is all of my possible samples, right? If I take a sample from this population of 3 flips of a coin, it has to be one of these 8 outcomes, has to be one of these 8 samples. I've just enumerated all of my possible samples. Again, I couldn't do this with a population of 500,000 people and a sample size of 20. That's way too many to enumerate every possibility, but I can do it with a simple situation like this. So I can look at my random variable X bar. For 3 flips, it has some different possible outcomes. It could be 0, 1/3, 2/3, or 1. Those are the only possibilities for X bar because, again, my population size is just so small that I can write out what all of my possible samples are. So these are the possible values for X bar. Again, these 8 outcomes are equally likely. We see 0 occurs 1 time out of 8. These are my probability of getting each of these X bars. 1 occurs 1 time out of 8. 1/3 occurs 1, 2, 3 times out of 8, equally likely, and 2/3, 1, 2, 3 times out of 8. You might recognize these like these ratios 1, 1, 1, 2, 1, 1, 3, 3, 1 from the Pascal's triangle, if you remember that, or from multiplying out x plus y to the first, second, third power. Or you might recognize these as the combinations. So there's a lot, this nice symmetry that we have here. There's a lot of other math behind it. But this is our distribution of X bar. Remember, X bar is our random variable. It's just the name of our random variable. And I want to do what I did before. I want to compute the mean, which is the random variable times its probability, make that column, add that column up, and that gives us our expected value of that random variable. 0 times 1/8 is 0. 1 times 1/8 is 1/8. 1/3 times 3/8, the 3's go away, and I get 1/8 again. 2/3 times 3/8, the 3's go away, I get 2/8 for that one. And I see my expected value of X bar, my expected value of this random variable is, well, it's going to be 4/8 or 1/2. And like before, we'll call this mu X bar. And just like before, we're going to calculate variance and standard deviation. So I need to calculate X bar squared. 0 squared is 0, 1 squared is 1, 1/3 squared is 1/9, 2/3 squared is 4/9. And then I need x bar squared times probability of x bar. So I'm multiplying these two columns. So 0 times 1/8 is 0. I have 1/9 times 3/8. One of the factors of 3 goes away. I'm left with 1 over 8 times 3, or 1 over 24. And then I have, for the next line, 4/9 times 3/8. Again, one of the factors of 3 divides out. And I'm left with 4 on the top and 8 times 3 on the bottom. That's 4 over 24. I'll leave it that way. So 4 over 24. And then lastly, I have 1 times 1/8. But since everything else is in 24s, instead of making that 1/8, I'll make it 3 over 24. Right? That's just rewriting 1/8 to be in a common denominator with the others. So what is the expected value of x bar squared? Well, that's going to be 4 plus 3 plus 1. That's 8 over 24. I think that is 1/3. Okay, then I need variance of x bar. Well, that's going to be expected value of x bar squared, 1/3, minus expected value of x bar, 1/2 squared. 1/3 minus 1/4 is 1/12. Anytime you have something like that, 1 over n minus 1 over n plus 1, it's 1 over n times n plus 1. That's how that all works out. And then the standard deviation of this random variable called x bar is 1 over square root of 12. The 12 has a factor of 4 in it. That can come out of the square root as a factor of 2, so that's 1/2. And then a 3 is left inside the square root. So it's 1/2 times 1 over root 3 for the standard deviation. Let's put this together with our previous two pieces of information and see what we get from that. So x bar for 3 flips when n is 3. We had still possibilities 0 and 1, but now we had 1/3 and 2/3, and these occurred in a ratio of 1 to 3 to 3 to 1. We saw that mu x bar was still 1/2, and that sigma x bar was 1/2 times 1 over root 3. Okay, so I think there are 3 things we can see here. Mu x is 1/2, and the mu x bars when n is 2 or n equals 3 is also 1/2. So when I look at the distribution of the average, the sample mean, it seems that the mean of the distribution of sample means is just the mean of the population. That kind of makes sense, right? If I take a bunch of sample means, well, I know that x bar is unbiased. So kind of on average, those x bars are going to be just the population mean. That's kind of what unbiased means. There's another calculation here. We saw this in chapter 5. It was a bit of a nuanced, detailed part of the proof, but or part of a couple of our proofs. But we saw that the standard deviation of an average was kind of like the original standard deviation, sigma x over the square root of the sample size. We see this is sigma x, this 1/2 out here. So this is like sigma x over root 2, or this 1/2 is like sigma x. This is sigma x over root 3, or really it's just kind of sigma x bar is sigma x over root n. We saw that before, but we see it come up again here empirically. And it seems like mu x bar is just mu x. But the other big kind of interesting thing that we see here is we started with a uniform distribution. And when we start averaging together flips, 2 flips, 3 flips, even that few number of flips, we get a distribution that is no longer uniform. Not uniform anymore. I think most of us would expect, and I certainly would have before I learned this, that if you average together uniformly distributed random variables, you probably should get like a uniformly distributed random variable at the other side. That just kind of makes sense. But that's actually not how it works. We actually see something that's starting to get a peak in the middle, tail off to both sides, and it looks kind of symmetric about its mean. We actually start to work our way from a uniform distribution, maybe towards something that looks like a normal distribution or a bell curve. That's I think it's a very unexpected result. We started with a uniform distribution just flat across, and when we start averaging together even 2 or 3 uniformly distributed random variables, we start to get something that peaks in the middle, tails off to the sides, where the endpoints are getting more and more unlikely, getting an average of 0 or 1 head on per flip on n flips is getting less and less likely to happen as n gets bigger. We get a peak in the middle and we maintain the symmetry. We might have expected that we maintain the symmetry. We kind of started with symmetry, but I don't think we would have expected a peak in the middle and tailing off to the sides. But if we really think about it, that kind of does make sense, right? If I think of something like, say, say a population of heights of people, whatever distribution it is, if I take a sample of size like 10 or 20, or even better yet, maybe a sample of size 100, right? If I take a sample of size 100, I'm probably going to get one person at like the 99th percentile, or a couple people at or above the 98th percentile, a couple really tall people. And if I take a sample of size 100, I'm probably going to get a couple really short people too at the 1st or 2nd percentile. If I just pluck one individual from the population and look at their height, I might just by chance get a really tall person or a really short person. But if I pick 100 people, I'm probably going to get a couple of really tall people and a couple of really short people, but I'm averaging the heights together. So when I average them together, they kind of average out, or their kind of center of mass is like kind of in the middle, right near the mean. They kind of average out to an average height person. And I'm going to get some kind of tall people and some kind of short people. And they're going to kind of collide, and they're going to kind of average out to a normal height person. And then I'm going to get a bunch of kind of, typical height people. So this is really the interesting new idea in the central limit theorem. So let's jump down to the central limit theorem and see what it says. The central limit theorem is across all of mathematics, probably one of my 3 favorite theorems, maybe my favorite theorem of all. I don't know. I always kind of go back and forth. But it's one of my 3 favorite theorems, definitely. And the central limit theorem says this. It says for large n, kind of like if you remember when we were talking about the law of large numbers, we had this like for large n idea that in the limit as the sample size goes to infinity, this thing is certainly true, but in practice, we have to say, what do we mean by a large N? What is a big enough N for this to approximately be true most of the time? So we need to address that, but for large N, for a big sample size, what are we saying something about? We're saying something about the sampling distribution of the sample mean. The sampling distribution of the sample mean is simply this idea that X bar is a random variable and it has a distribution, right? X bar, the sample mean, is a random variable. It has a distribution. We call that the sampling distribution of the sample mean. And it's just a more wordy way of saying the distribution of the random variable that we call X bar. Just like we did up here, right? We had random variable X bar, and here was its distribution. Or this other random variable X bar for two flips, there was its distribution. These were sampling distributions of the sample mean in these different cases. So for large N, the sampling distribution of the sample mean, the distribution of X bar, when taken from replacement, or taken with replacement, sorry, from a population with mean mu x and standard deviation sigma x. So if we know the underlying population's mean and standard deviation, like we did up here, remember this was where we started. This was the underlying mean and standard deviation. So for large N, the distribution of X bar, where that or a sample is coming from a population with mean mu x and standard deviation sigma x, for that we can say the following. The big thing here is that this is approximately normal, approximately a normally distributed random variable. Right, so X bar is approximately normal. X bar is mean, mu X bar is going to be mu x. If I take a bunch of sample means and average them together, I would expect to get something pretty close to the population mean. That's because it's unbiased. But we also kind of demonstrated that above, and we proved that carefully in a previous lecture. And the standard deviation decreases with the sample size. With a bigger sample size, the volatility of X bar, how far X bar can kind of deviate from what it should be in a sense, mu x, gets smaller and smaller. That makes sense. If I have a larger sample, X bar is a better estimate of mu x, of the population mean, and it should have less volatility. It shouldn't be able to swing around as much. It should stay closer to mu x if I have a really large sample size. So these things we have seen before, but it's always good to see them again. We also saw them empirically just now. But the real surprise here is that this is approximately normally distributed. Keep in mind, we didn't say, taken with replacement from a normally distributed population with mean mu x and standard deviation. We didn't say that. From a population. This population could be uniform. It could be normally distributed, could be uniform, could be exponential, it could have skewedness, it could be bimodal. This population can have whatever distribution we want. And when we take averages, they tend to normal. So some additional thoughts or notes here. The first kind of elephant in the room is, what do we mean by large N? I mean, this is nice for large N, or, in math speak, in the limit as N goes to infinity, but we don't have time to sit here and take infinitely large sample sizes. So what do we mean by that? In other words, give me a value of N, give me a number for N where I can say the following. I can say that for most situations, for most populations, a sample size this large, for most applications, for the degree of accuracy I need for most applications for me to be happy, this sample size will be big enough that I can use the result of the central limit theorem and be within the accuracy bounds I need in most cases under most populations. That rule of thumb is N bigger than or equal to 30. If we have a sample size of 30 or more, that's a statistical rule of thumb. It's a heuristic. It's basically like saying this works most of the time in most situations, so you're probably not going to regret your choice too often if you go with n equals 30 or above. So if I have a sample size of 30 or more, then I feel confident in applying the result of the central limit theorem. Or if I start out with a normal population, then this applies exactly for any n. And we'll see in a minute why that's true. And as I mentioned before, I'll talk about caveats maybe in a second here, but as I mentioned before, that really the magic of this theorem is that it doesn't matter what the underlying population's distribution is, essentially, effectively. You could pick any distribution you want for the underlying population, and averages will converge to a normal distribution. Now, to be fair, that's where the caveats come in. If we have super wonky distributions to start with, and maybe then n equals 30 isn't going to get us a result that we're happy with. So particularly if I have a very large degree of skewedness. So if I'm looking at, say, the Powerball lottery, an extremely small chance of winning an extremely large amount of money. And then I don't want to say, okay, if I average together 30 tickets, then, then I expect to have a normally distributed result. I wouldn't want to say that in that case, right? So there are some caveats. So if I have a lot of skewedness, I might question this, this rule of thumb. I might question whether a sample size of 30 is good enough or whether I might need a much larger sample. But at least in theory, we don't care about the initial distribution. In practice, we might, but in theory, all distributions means converge to a normal distribution. So the natural question then is, well, why a normal distribution? Why not a uniform distribution or an exponential distribution or some other distribution? And there's a really interesting answer to this. It's a combination, I think, of an interesting answer and also a really elegant piece of mathematics. So the kind of interesting answer is that the normal distribution is what we call an attractor. And the way that I like to describe this, is if you think about pool balls bouncing around on a pool table, not a billiard table, but a pool table with the pockets in it, right? If you bounce a ball around really hard, if you give it a lot of energy, it'll bounce around quite a lot. It'll kind of bounce all over the place. But eventually, just by chance, it's probably going to fall into a pocket. Once it falls in the pocket, it doesn't bounce around anymore. It stays in the pocket. So the pocket on a pool table is kind of like an attractor. If you get really close to the pocket, if the bottom of the ball starts to go over the little lip of the pocket, it's going to fall into the pocket. It might take it a while to kind of make its way around the table, but eventually, if you give it enough energy, it's going to bounce around long enough that it eventually goes into a pocket and then never comes out. So kind of like if you get sucked into a normal distribution, you can never get away. It's like a black hole almost. So then we might say, okay, well, like there's 6 pockets on a pool table. Maybe the normal distribution is an attractor, but also the exponential distribution is an attractor. And, populations that start looking like a normal distribution maybe converge to a normal, but things that look like an exponential originally converge to an exponential. Can't something like that happen? And the answer is basically no, because the normal distribution is the only one of these kind of attractors with finite variance. There are others. There's, for instance, the Cauchy distribution has this property, but it has infinite variance. The physicists love the Cauchy distribution for things like astrophysics and things. They're really interesting applications, but it has infinite variance. And when we made this statement here, standard deviation sigma x, by implication, that's saying we can write down what the standard deviation is. It's not going to be infinity. So the normal distribution is the only attractor with finite variance. And a little interesting mathematical deviation here, just I know that I'm going to explain this very hand wavy, but I just think it's the really coolest bit of mathematics and part of the reason I like the central limit theorem so much. So there's this idea of stability of distributions. And it's kind of related to this idea that that there are some distributions where if I take sums or averages of them, if I take averages of normally distributed random variables, they stay normally distributed. And then there are some distributions that have finite variance and some that have infinite variance. And there's this important parameter called alpha. So it's called alpha stability. So this letter alpha comes up, and the letter alpha can be some real number above zero. And it turns out that, uh, and I can never remember which way this goes. I'd have to think about it. I always kick myself for not thinking about it ahead of time whenever I get to this. I should have thought about it before class today, um, but it goes either this way or exactly the opposite. So I'm either right or I'm exactly wrong. So I don't know what that says. Um, but it's something like this. It's like if alpha is between 0 and 2, so strictly above 0, but less than or equal to 2, then we have the attractor property. And if alpha is bigger than or equal to 2, we have the stability property. Or sorry, we have the finite variance property. So this stability property, this kind of attractor property, is, let's say, from open 0 to closed 2, and the finite variance property is from closed 2 up to infinity. For us to have both properties, the finite variance and the stability property, the only overlap between open 0 to closed 2 and closed 2 up to infinity is exactly at 2. And if I look at the alpha equals 2 distributions, the only distributions that can be both finite variance and attractors and have this stability idea, alpha equals 2, if I look at those distributions, those are exactly the family of normal distributions. Those are exactly the distributions with a PDF that looks like the normal distribution, where I have this like e to the negative stuff squared. And I just think that's the coolest thing. It's like you have these two seemingly very different ideas. They both relate to this one number. And on one hand, to have one property, the number has to be less than or equal to 2. And to have the other property has to be greater than or equal to 2. And the only overlap is exactly at 2, which plucks out exactly the normal distribution family. So why normal? That's why. This kind of seemingly magical property of Levy alpha stable distributions sitting right there at alpha equals 2, just that perfect, walking that tightrope between not having infinite variance and still being an attractor sits the normal distribution. So that's why I like the central limit theorem so much. Such an elegant little mathematical fact or detail, and it feels like, the normal distribution, if it had, leaned a little bit too far to the right, it would have had infinite variance, or leaned a little too far to the left, it would have not been stable anymore, but it's just right there at the perfect place. And it's the only one that's like that. There are distributions that are attractors or that have the stability property, like the Cauchy distribution, but they have infinite variance. And most distributions do not have this stability property. Like you take a uniform distribution and you add up uniform distributions, just like we saw empirically up here, we do not get uniform distributions back out. We get something else out. So a rule of thumb is sample size bigger or equal to 30, we can apply the result of the central limit theorem. Or if we have a normally distributed underlying population, we can apply central limit theorem without concern for the sample size. Why is that? Well, it comes from the fact that the normal distribution has this stability property. That if I have two normally distributed random variables and I add them together, or if I average them, which is essentially just adding them together, I get exactly a normal distribution out. Right. Really, the big thing that the central limit theorem says is this normal distribution property. We showed both of these earlier, and these didn't really have any regard for the underlying distribution. For the standard deviation to work out right, we had to have independence. But, this mu x bar equals mu x and sigma x bar equals sigma x over root n, those are basically just arithmetic arguments or algebraic arguments. So really the big thing that the central limit theorem says has to do with this normality here. So when is X bar normal? Well, it's approximately normal for sample sizes bigger or equal to 30, regardless of the underlying population, essentially. But it actually is exactly normal by this stability property of the normal distribution if the underlying population is normal. As a side note, when we look at testing for normality in the supplement that I mentioned before, this is one of the reasons we care about testing for normality. If I have a population, I have a sample, and I want to know, do I think this sample comes from a normally distributed population? If it's a small sample and I want to apply central limit theorem, if I have good reason to believe the underlying population is normal, I can apply the result of the central limit theorem. But if not, then I can't. So this might be one reason that we want to know whether we think the underlying population is normally distributed. So as I just reiterated, if the population is normal, central limit theorem result holds for all n, no need for n bigger than or equal to 30. And I don't know if this is a very common term, but I would argue that the central limit theorem could just as well be called the fundamental theorem of statistics. You might have heard of like the fundamental theorem of algebra that, n3 polynomials have exactly n roots, counting multiplicity and counting complex roots. And like that theorem is really foundational to algebra, or there's like the fundamental theorem of calculus that says something really fundamental and important about calculus. I would argue this is the fundamental theorem of statistics. It's really the basis for chapter 7, confidence intervals, for developing these confidence intervals, and for chapter 8. It's really the basis for inferential statistics. Okay. One of my undergrad math professors basically said, I mean, this is pushing it a little far, but he said something like, if you do a PhD in statistics, your thesis will simply be proving the central limit theorem in some weird special case. like that's how fundamental it is that your thesis will be directly or indirectly essentially just a new proof of the central limit theorem that this idea applies in some other case, or that some closely related idea applies in some closely related special case. So that's how important this is to statistics, to our ability to essentially take this probability, this purely mathematical abstract structure, and apply it to real world ideas to solve real world problems. This really is the link. It's kind of where the rubber meets the road in some sense. We developed this, this car, this probability, but it doesn't have any wheels. We can't actually make it move forward in reality. It's a nice car. It works really well. It's kind of cool, but doesn't actually go forward until we put the central limit theorem on it. That's like the wheels that let it move forward. Okay. So this was the central limit theorem applied to the sampling distribution of the sample mean, the distribution of X bar. But if I have a sample, one descriptive statistic for that sample is X bar, what's the sample mean? I could have other descriptive statistics as well. For instance, I could have p hat, the probability of an event. Right, if I have, even thinking back up here, if I have a sample, say of size 3, I could ask what's my empirical probability of flipping a heads if I got this sample. I got 2 successes on 3 tries. I got 2 heads on 3 flips. So my kind of empirical estimate for the probability of flipping a head would be 2/3. Happens to be the same as X bar observed in this case, but that would be my estimate for the probability of flipping a head. So suppose we're interested in some population proportion, probability of some event, probability of success, and we estimate that by p hat, the number of successes observed in n trials. we have data from n trials, we have n outcomes, y1 through yn. So this might be like, heads, tails, tails, heads, tails, something like that for y1 through y5. And then we construct our x's by saying x1 is, for instance, 0 if y1 is not a heads, or it's 1 if y1 is a heads. And x2 is 0 if y1 is, or if y2 is tails, and 1 if y2 is heads, and so on. The expected value of x, we've discussed this before, so that's why I'm not going into a ton of detail here. The expected value of x, or mu x, would be p, and the standard deviation of sigma x would be root p1 minus p. And we note that p hat is simply the sum of the x's divided by n. It's really just x bar. So here our y's are the original outcomes, but then we've passed through this random variable x, and we see that really p hat is just the same as x bar. It's just really a sample mean. It's a sample mean of a random variable that is related to the original y random variable. So what can we say about the sampling distribution of p hat, the estimator for p? Well, replacing x bar by p hat, replacing mu x by p, and sigma x by root p1 minus p, we just use our previous central limit theorem and apply to this new scenario. For large n, the sampling distribution of p, namely p hat, the sampling distribution of p hat, namely the distribution of the random variable p hat, is approximately normal with mean p and standard deviation root p1 minus p over n. Note that this is root p1 minus p over root n, or this is sigma over root n. And then we just put it all under the same square root. Right? We have a square root on the top, a square root on the bottom. We can just wrap that all under the same square root. Geez, there's a thunderstorm going on outside my house that's like, the thunder is rattling the windows. Hopefully I don't lose connection here. Am I still? Okay. My meeting is still up and everything. I haven't lost haven't lost power yet, and haven't lost internet either, so that's good. Okay, and the rule of thumb for proportions is a little bit different than the n bigger than or equal to 30. It's kind of dependent on our estimate of the probability of success. In other words, we say that n is large enough for the conclusion to apply, for this normality to apply, if we expect to have essentially what amounts to at least 5 successes and at least 5 failures. Right? So like I need to have enough coin flips to expect at least 5 heads and at least 5 tails. So like 3 flips or something probably wouldn't pass muster here. But if I had 10, 12, 14 coin flips, and if I think that my probability of heads and probability of tails are somewhere close to 50-50, yeah, I should be expecting about at least 5 heads and 5 tails from say 12, 14, something like that, coin flips. So we see that if p and 1 minus p are both kind of near 1/2, we can actually get away with a much smaller sample size than size 30. Maybe something like size 10 to 15 would be good if p and 1 minus p are both fairly close to 1/2. But on the other hand, if p was like 1%, if it was extremely unlikely to get a success, well, then to have NP bigger than or equal to 5, or n times 1% bigger than or equal to 5, I would need like a sample size of 500. So this rule of thumb is quite dependent on the size of p and 1 minus p, the likelihood of success or the likelihood of failure. For ones near 50%, a fairly small n will do the trick. For probability of success or failure near, 0% or near 100%. We need a much, much larger sample size to kind of flesh that out, right? I mean, think if you're saying one of the classic examples in a situation like this is like, the number of typos per page in like a well-edited, published book. Like, you pick up I don't know, a copy of The Lord of the Rings or something like that, and how many pages do you have to expect to go through before you find a typo? Probably a whole lot, right? So the chance of finding a typo on a given page is probably quite small. I would have to sample a lot of pages and check off either typo or no typo on each page, maybe 1,000 pages or something, uh, to really have any idea uh, about what that distribution looks like. But on the other hand, if I'm just flipping, a coin that I pick up out of my chain, it's probably got close to a 50-50 chance of coming up heads or tails. I could probably be happy with 10, 15, 20 coin flips, and that distribution would be very informative. Okay, let's look at a couple examples. I kind of just realized I had my full screen up the whole time, but we haven't used the z-score table until now, but we will be using it now. So let's take a look at this example on SAT scores. Let's assume the national average SAT score, math plus verbal, is 1028, and the population standard deviation is known to be 100. And we have three parts here, A, B, and C. If the scores are normally distributed, simply compute the probability X, a normal distribution is bigger than 1050. This isn't a central limit theorem question yet. We're just doing this in preparation. So compute the probability that a single student's score is above 1050. So here is X, a normal with a mean of 1028 and a standard deviation of 100. So the mean of 1028 is here. My inflection point, 100 to the right of 1028, is at 1128. And 1050 is somewhere in between these two. And I'm looking for a probability X is bigger than 1050. So I'm looking for the area to the right of 1050. I know that this is going to be less than 50%, but probably only a bit less, right? It's not going to be like 1%. This is my kind of 0 to 1 standard deviation range here. And my number is 1050 is within that. It's within 1 standard deviation above the mean. So I expect to have a substantial probability here, not above 50%, but probably not like a couple percent either. What's my standard approach here? I reframe the question in Z, mean of 0, standard deviation of 1. Z is X minus the mean, 1028, over the standard deviation of 100. My numerator is 22 divided by 100. That's 0.22. So I can rephrase this as probability that Z, the standard normal, is bigger than 0.22. This is a right tail area. My table gives me information in terms of left tail area, so I need to flip this around. I suppose I'll use symmetry here, flip everything about 0. So this 1 flips to -1. The positive 0.22 flips to a negative 0.22. And my right tail area flips over to a left tail area. And that is a negative 0.22. The negative kind of blended in with the 0 there. And this is probability z is less than, the direction changed, and the sign changed, negative 0.22. I'm on my negative z-scores table, and here is my negative 0.2012. So it looks like this is 41.29%. So about a 40% chance or 2/5 chance that a student scores above 1050. Now, again, this was just a regular old normal distribution problem. So we didn't use central limit theorem yet. Now, here's the key word. When I start talking about averages of certain numbers of students, that's cluing me into a central limit theorem problem. So part B sounds pretty similar. Compute the probability that the average of 30 student scores is above 1050. In other words, compute the probability that X bar, that's an X bar there, is bigger than 1050. Well, here I notice that X bar by the central limit theorem, my sample size is at least 30, is approximately normal with some mean mu X bar and some standard deviation sigma X bar. Right, my central limit theorem tells me since n is bigger than or equal to 30, I can apply the conclusion that X bar is approximately normal. My mean stays the same. Mu X bar is just mu X. And my standard deviation sigma X bar is sigma X over root n. So mu X bar is mu X, the underlying population mean, or just 1028. This is just mu X. And sigma X bar is sigma X over root n, or that is 100, the original population standard deviation, over root n, or root 30, the sample size of 30. Let's figure out what that is. 100 over square root 30. So about 18.3. Now I want to know what's the probability X bar is bigger than 1050, but once I do this, step here and apply the central limit theorem, well, now this is just the normal distribution question, right? I just have some normal distribution with a mean of 1028, a standard deviation of about 18.3. I want to know what's the probability that this normally distributed random variable with this mean of standard deviation is above 1050. So this is the distribution of X bar. This was the distribution of X, the underlying population distribution. This is the distribution of X bar, the distribution of, or the sampling distribution of the sample mean for a sample of size 30. And I'll write this again down here. Still centered at 1028. My mean is kind of stable. It doesn't move around. But now a standard deviation is only 18.3 units. So what's 1028 plus about 18? That's like 1046 or so. So now my inflection point here is at something like 1046. Just trying to squeeze my numbers all in here. 1046. Where up here, this inflection point was at 1128. So really, this distribution is actually much narrower and steeper than the one above. Let me actually adjust it now that I realize that to look a little bit more in line. It's still not going to be, perfect, but so that when I look at the previous one compared to this one, it does look a little bit more reasonable. So 1028 up to, what did I say, 1046 or so. And now if I look at 1050, I know that my 1050 is still a little bit off here, but if I look at 1050, the area to the right of that, I see them more than one full standard deviation to the right. Before I was kind of in between 0 and 1 standard deviations. Now I'm more than one full standard deviation to the right. So what's probability that X bar bigger than 1050? Just like before, my next step is to reframe this as a question in Z. My associated Z score, 1050 minus the mean of 1028, over the standard deviation of X bar, which is 18.3. Or I could write it as over 100 over root 30, if I wanted to write it that way. In other words, this is 22 over 18 point. What happened to my calculator here? 22 over 18.3, or about 1.2. So now in Z, I'm looking at 1.2 is my Z index, and the area to the right of that. I see this is going to get much smaller. My score didn't change. The score of 1050 that I'm looking at didn't change. But when I'm looking at one individual student, I might get somebody who scored quite high or quite low. But if I'm looking at the average of 30 students, I'm probably going to get one person who scored high and one person who scored low, and they kind of average together and pull everybody closer to that 1028. And the student who scored a bit high and the student who scored a bit low, again, kind of average together towards 1028. So to get above 1050, we would have needed to get a bunch of students who scored a bit high or pretty high, and not very many students who scored a bit low or pretty low. That's going to be less likely to happen. So now probability X bigger than X bar bigger than 1050 is probability Z bigger than 1.2, or probability Z less than negative 1.2. It's the same change as up here, so I'm not going to rewrite everything. But probability Z less than negative 1.2, here's negative 1.20, is 11.51%. Okay. So it's much more likely to get an individual student who performs, substantially better than expected, maybe, than it is to get 30 students who, on average, perform substantially better than expected, right? Or let's look at part C, and then I'll kind of expound on that a little bit more. Part C computes the probability that the average of 200 students scores is above 1050. Well, this is very similar to the previous ones, except that now we have an even tighter distribution around the mean. So here's 1028. X bar is approximately normal. Mu x bar is still mu x of 1028, but sigma x bar is sigma x over root 200, or that's 100 over root 200. Let's see what that is. So that's about 7.1. So 128 plus 7 is like, or 1028 plus 7 is like 1035. Plus another 7 would be like 1042, plus another 7 would be like 1049. So 1050 is actually now 3 standard deviations above the mean. 1050 is now like way out into this tail. This should be quite a small probability. So what is probability x bar bigger than 1050? Well, my associated z-score is 1050 minus 1028. That numerator is the same as it has been. My denominator now, 7.1. 22 over 7.1 is going to be a little more than 3. Right, so now we're 3 standard deviations above the mean, much less likely to happen. About 3.10. And I won't write out in as much detail as I did before, because this is basically the third time we're doing the same problem. And what's probability z less than negative 3.1? We see that that is 0.0010. So 0.1% or 1 part in 1,000. So we went from like 4 in 10 to 1 in 10 to 1 in 1,000 by just increasing the number of students that we're averaging together. We still had a distribution centered at 1028. We still were looking for folks scoring above 1050, but are we looking at the likelihood an individual scores above 1050, the average of 30 students scores above 1050, or the average of 200, right? Or another way to look at this is, if I was suspicious that maybe there was some cheating going on, if I saw an individual score above 1050, that wouldn't set off alarms at all. It's perfectly likely to happen. If I saw one person's entire class of 30 students score above 1050, it might be a little bit suspicious, but really not much. 1 in 10 classes is going to score above 1050 on average. If I saw like an entire school class, like not just like classroom class for 30 students, but like a whole, all of the, juniors in a certain school or something, 200 of them on average scored above 1050. Well, now I'm pretty suspicious. That would only happen like 1 in 1,000 times. So if an entire school's like, junior class of 200 students who took the SAT, if their average scores were above 1050, then I might be a little bit suspicious or fairly suspicious that some cheating was going on and investigate further. Right? That would be quite unlikely to happen just by chance. Now, again, that doesn't mean necessarily that cheating was going on. Maybe that school just has a really good SAT prep program or something like that. But it would at least be suspicious, and I would look for something to explain why something so rare has occurred. And also, it is important to note that this is where we're working our way closer to inferential statistics. 1 in 1,000 chance isn't likely, but it happens 1 time out of 1,000, right? And certainly there are a lot more than 1,000 schools with a bunch of students taking the SAT. So 1 in 1,000 seems unlikely until you look across the country and you say, oh, there's, whatever, 100,000 schools or something that, high schools across the country, however many there are, it wouldn't, but if there's 100,000 schools across the country, well, probably 100 of them are just by chance going to have something like this occur. And also probably 100 of them just by chance are going to have the opposite occur. So if this year's junior class, across one school does quite terrible and you say, oh, that's in like the bottom 0.1%. Well, I mean, that school could have just got a bad luck of the draw this year. So anytime we're making inferences, there are always these caveats. We're not making formal mathematical proofs that something is certain to be true or certain not to be true. We're making kind of empirical arguments. We're making statistical arguments. We're saying the weight of the evidence is in this direction, but we can't conclude anything with certainty. So that's kind of that's always the statistician's cop out. It's like, well, the evidence points in this direction, but we can't conclude it with certainty. So, do with that what you will. Some people would say that that means the statistics is useless. Some people would say that, some people lean much too heavily on statistics and say, oh, it's unlikely to happen, therefore you definitely cheated. I don't think either one of those is really a proper interpretation of these kinds of statements. Take it as a piece of evidence as part of the whole, and then make a judgment on the basis of all of the information available. All right, and let's look at this second example. We won't quite get to chapter 7 confidence intervals, but we will pick up there next time. So like I said, take a glance through 7.1 and 7.2 on confidence intervals before next time, and you'll be primed that way for this material where we're starting to bring together the descriptive techniques in chapters 2 and 3 and the mathematical probability techniques in chapters 4, 5, and 6 into something where we're making inferences and marrying those two ideas together. Okay, so let's look at example 2. An elevator is rated at 3,125 pounds, which is, say, 2,500 plus a 25% safety factor. And it states a maximum safe occupancy of 16 passengers. So did you ever get in an elevator and see that? It says a weight and number of passengers. We know that generally speaking, men have weights that are heavier than women. So we'll ask basically the question, is this safe? Is this elevator likely to be safe if 16 men were to get on the elevator? So men have weights that are normally distributed with a mean of 182.9 and a standard deviation of 40.8 pounds. If 16 male passengers get on the elevator, what's the probability it's overloaded? If this is a fairly high number, then something seems off with our claims up here. We either need to beef up the elevator so we can increase this number so that it's unlikely the 16 passengers will overload it, or we have to decrease the number of passengers that we're saying it's safe to hold. We might have to say, it only holds 12 passengers instead of 16, decrease that number so that it's in concordance with this one. On the other hand, if we look at the probability that we're overloaded with 16 male passengers and it's fairly small, then maybe we're okay with that. It's unlikely that 16 male passengers will actually overload the elevator at this level. So let's see which situation we're in. Okay, so what do we have here? Well, I can say, let's consider that y is, well, let me back up one. Let me say that x is the weight of one male passenger. So x is normally distributed with what? Mu x is 182.9 and sigma x equals 40.8. And my question is, what's the likelihood that the 16 male passengers overload the elevator? In other words, if I make a variable y, which is x1 plus x2 plus so on, plus x16. If I add up the 16 draws from this normally distributed population, what's the probability that y is bigger than 3125 pounds? Right, so this is really our question. What's the probability y is bigger than 3125? As I mentioned before, we actually could have constructed and framed the central limit theorem in terms of sums of random variables instead of averages of random variables, but it's kind of annoying because then like mu x bar or mu sum of x is going to look like n times mu x, and you just have extra bits floating around where they don't need to be. So let me reframe this problem back so that it looks like the central limit theorem. The sum of 16 people's weights is bigger than a number if the average of their weights is bigger than that number divided by n. So x bar is x1 plus out to x16 over 16. Remember, this is a random variable. The average of 16 randomly chosen people's weights. And I can reframe this question as probability that x bar is bigger than 3125 over 16. So this is really the question that I'm going to try to answer here. What's the probability that the average weight of 16 men chosen from this population is bigger than this number? So what's 3125 over 16? Let's see. So that's about 195. So that's what I need to know. But x bar is normal. Why is it normal? Our sample size is not bigger than 30. However, the underlying population distribution is normal. Since the underlying distribution is normal, I can apply the result of the central limit theorem without consideration of how big the sample is. So x bar is normal with mu x bar equals 182.9. And sigma x bar equals sigma x 40.8 over root 16. Or that's 40.8 over 4, or that's 10.2. So I have 182.9 here. And my question is, what's the probability x bar this distribution is bigger than 195? So probability x bar bigger than 195. And as usual, we're running out of time, so I'm going to do this a bit quickly. Z is 195 minus 182.9 over the standard deviation of 10.2. So I have 195 minus 182.9 over 10.2 is 1.19. So this is probability Z is bigger than 1.19. I would recommend going through this carefully on your own and, kind of confirming to yourself that everything I'm doing here is correct. That's a right tail area, so we can switch it to a left tail area with symmetry. We make a left tail area with probably Z less than negative 1.19 because we had to flip over 0. And probability Z less than negative 1.1. This is the row we're in. And we want the column corresponding to 900ths is 11.7%. So a 1 in 10, 1 in 9 chance that we're overloaded. If 16 men were to get on this elevator, that's probably a bit too high of a chance. So we might want to either push this number down a little bit, right? If we were to ask for the sample of ask for a sample average of 15 or 14 people, that would give a different distribution. We'd have a different number that we'd be looking at here because we'd be doing 3125 over 15 or over 14. And that would give a lower probability of being overloaded. Or the other thing we could do is we could beef up the elevator. If this 3125 went up to 3500, that would give us a bigger numerator here, a bigger number here. That would push us further out in the tail and also reduce the probability of being overloaded. So we should either reduce the number of passengers that we're claiming it's safe for, or we should increase the safety rating of the elevator, one of the two. And now practically, like if you've ever seen those ratings on elevators, it's like, you know, a 5 foot by 5 foot elevator, and they say, you know, maximum occupancy 16 people. It's like you couldn't get, you know, 16 clowns that can fit in a clown car in an elevator that size. So is this a practical problem? And should you be worried about elevator safety? No, but just as an example. Okay, when we come back, we will start into chapter 7, confidence intervals, and start really what constitutes something like the third segment of the course, where we're looking at inferential statistics. We looked at descriptive statistics, probability, the mathematical structure, and then now we're moving to inferential statistics starting next week. So that is what I had for you today. Let me stop the recording.